So one of the ways in which we can understand algebraic structure is we can understand it from a point of view of kind of having a set of nouns and a set of verbs. It's almost like having a set of Lego blocks that we can work with and also a set of rules for how those blocks fit together with one another, right? If we have those two things, if we have a complete enough set of those two things, we should be able to do algebra. In other words, simplify an expression by sticking those blocks together, and also ideally solve an equation by taking apart some of those expressions into their individual component parts until we have just the block that we're looking to solve for, right? And that is kind of the generators and relations viewpoint of algebra. When we talk about generators and relations, we talk about a set of objects. They're like the building blocks of our algebraic structure. Those are called the generators. And then we talk about a set or a list of relations. And relations, each relation is just a specific kind of expression, algebraic expression, built out of the generators. Right? And we decide that that expression has value equal to the identity element. So it's an expression that we may cancel. There's another way to think about what relations are. Relations are cancellation rules. They tell me what I can cross out in an expression if we want to be as crude as our algebra students usually are, right? Oh, just cancel it, just cross it out. And usually we like to say, no, it's really about simplifying it. It's really about evaluating it. It's really about, dividing something by itself or whatever. And we know what we're talking about. We're all math teachers here. So we'll just say these are cancellation rules. These are things that when you see that expression, you can just toss it out the window because it's equal to the identity element in our group, and therefore multiplying by it or not is an invisible operation. So we can choose to see it, or we can choose to cancel it and not see it. So formally speaking, when we have a set of generators and a set of relations together, they form what's called a presentation for a group. A presentation lists a set of elements that are called generators, and there might be a finite number of them, there might be an infinite number of them. It really depends on your algebraic structure. But we think of those as being the building blocks. Generators are the building block elements. They're like the letters of the alphabet, right, with which we can make a word that hopefully that word is meaningful in some way. Right? But then together with those, we also have a list of what are called relations. And relations are nothing more than a list of expressions that are built using those generators. If we think of the generators as forming like the alphabet for our language that we're making here, then each expression is just like a word that's spelled out of that alphabet. And a relation is nothing more than a word written with the generators, written with our alphabet, that we decide that word is equal to the identity element in my group, right? Just from a definitional perspective. These are the things that we can just cancel anytime we see them in one of our expressions. So generators together with relations, that forms a presentation for a group. If the set of generators is a finite set, then we'll call the group a finitely generated group, naturally. If the set of relations is also finite, then we'll say that the presentation of this group is a finite presentation, or that G is a finitely presented group. So as you might expect, the examples that we're going to wrestle with in our course this semester, because this is not a full-bore, full-ahead sort of group theory course, all of our examples will be finitely presented, examples of finitely presented groups. At the very beginning of our course, we worked on some examples of algebraic structures that had just 4 elements in them. And there were sort of 4 different examples that we looked at. We called them the 4 fours. So the first of those structures was a group in which the operation was multiplication of complex numbers. So we had 1, -1, I, and -I with the usual multiplication of complex numbers operation, where I times I is equal to -1. And so at the time, we just generated a Cayley table for that one. The same thing with the second group, which was made out of the integers from 1 through 4 with the operation of multiplication modulo 5, right? So we multiply the numbers together, and we only keep the remainder of that product after dividing it by 5. Right? That also formed a group structure that we used 1, 2, 3, and 4 to represent those elements. The third was an example where we had these sets of cardinality at most 2. So the empty set, a singleton set A, a singleton set B, and then the set consisting of A and B together. And the operation was the operation of the symmetric difference of sets, right? Which was this was the one that I think broke our brains the most to think about, because we're not used to thinking about set arithmetic in that way, but it forms an algebraic structure because we have closure, identity inverses, associativity, all the things that satisfy the definition of a group. And so you were able to build this Cayley table for that set structure. And the fourth was matrix multiplication. We had these 2 by 2 matrices, 4 of them in all. Their products equal one another, right? We have closure. We have an identity element, which was the identity matrix. We called it A in this table. Everything had an inverse. Associativity is always true about matrix multiplication. And so all 4 of these formed group structures that had 4 elements in them. And so it's a valid question to ask, can we, or how can we, express these groups in the language of generators and relations? What are the raw materials in each of these 4 groups, and how are those raw materials related one to another? When we studied the 4 fours at the beginning of the semester, the main question that we had was which one of these 4 groups is not like the other 3. Do you remember which one of these 3 was the odd one out? So when we did this activity, we singled out this weird oddball sets and symmetric differences structure as being different from the other 3 because you noticed that every one of the elements here was its own inverse, as opposed to the other examples. I'm going to use maybe the first group here, where there are elements that were not their own inverses. For example, I is not its own inverse. If I multiply it by itself, I times I don't get the identity element of the group, which is 1 in this example. Instead, when I multiply I by I get -1, right? Not the identity. And so that was the fundamental difference, right? The real beneath the surface difference between the third group and groups 1, 2, and 4. And groups 1, 2, and 4, it turns out, are actually kind of pretty much the same as one another as far as we could tell, right? So let's take just a moment and see if there's a way that we can express. Let's start with groups 1, 2, and 4, right, the ones that are all the same as one another, how to express them in terms of generators and relations. Then maybe we'll also look at how to do the set example using generators and relations. So thinking about that first group, the one with the complex numbers 1, -1, I, and -I, right? The question is there a single element in that group that can generate, whose powers can generate as many of the other elements in the group as possible? Right? So looking back at the Cayley table for just a moment. What happens, for example, if I take the element -1 and I multiply it by itself? I end up getting just the identity element. I get back to 1 itself, right? If I multiply that by a -1 again, I'm going to get back to -1. If I multiply by -1 again, I'm going to get to 1. So the powers, the successive powers of the number -1 are just going to account for 1 and -1. They're never going to get me the I or the -I just by multiplying the -1 by itself. Right? So -1 is not powerful enough, pun possibly intended, to generate all 4 of the elements of the group. On the other hand, if I take I, for example, and I multiply it by itself, I times I is going to give me -1. And then if I multiply by another power of I, -1 times I is going to give me -I. If I multiply that by another I, -I times I is going to give me +1. Multiply that by I again, and I get back to I. Right? So the successive powers of the element I actually account for all 4 of the elements in my group. The first power of I is I, the second power is -1, the third power is -I, and the fourth power is the identity element. So in fact, I can be thought of as a generator for all 4 elements of the group, right? Because its powers cycle through all 4 of the elements in my group. So we might think of I as being the raw material, right? If I have I, then because I also have closure in my group, I have every power of I in my group as well. And every power of I accounts for 1, -1, I, and -I, so I get my entire group. Right? So I is a complete set of generators. The set consisting of I is a complete set of generators for my group. And we might say that a relation for this group, so what can we cancel? Remember, what is equal to the identity? Well, the fourth power of I is equal to the identity. And so we would say that the fourth power of I can be thought of as in fact, the relation, the only relation that we need in order to describe this structure. So a presentation of this group would be, it would consist of the generator, I, which we write in this sort of notation here, right? We put angle brackets, and then the generator list of generators, so just I. And then afterwards we list whatever relations that we need, right? Whatever expressions that we want to be able to cancel. And here that's just I to the fourth is equal to 1. If we try that same process with the other structures, we can check that, for example, this structure with the residues mod 5, 1, 2, 3, and 4, and multiplication modulo 5, we can check that the powers of 2, for example, actually generate every element in this group? Somebody want to check me on that? So how can I be so sure that 2 actually is an example of a generator for this group? So when you take the successive powers of 2, and by powers we mean use the operation of the group to combine 2 with itself repeatedly, right? As we take those successive powers, we end up accounting for all 4 of the elements in this group. 2 times 2 mod 5 is equal to 4. Times 2 mod 5 is equal to 3. Times 2 mod 5 is equal to 1. And so we get all 4 of the elements of this group just by taking successive powers of 2. So how I would say that, right, is I would say that we can represent this group as having a generator of 2 with the single relation 2 to the 4th power is equal to 1. Right? Similarly with our matrix multiplication group. This was G4. Right? That this group, it turns out, we can single out a single matrix. Let's say this matrix B, 0, -1, 1, 0. Right? Using the Cayley table that you came up with here, we can easily read off B times B, B squared, is equal to C. Then if I multiply that by B, C times B is going to give me D. If I multiply that by B, D times B is going to give me A, which is my identity element, because after all, when I multiply A by B, I'm going to get B again. Right? So here, just by using the Cayley table, we can check that the successively higher powers of B, this matrix 0, -1, 1, 0, are also going to account for all 4 of the elements inside this group. And so at the end of the day, having presentations for these 3 groups actually gives a pretty compelling argument for why not just did these groups look the same when we wrote down their Cayley tables, we're showing now kind of exactly in what sense they are the same. Right? Each one of them we can write as a single generator, I or 2 or this matrix 0, -1, 1, 0, and a single relation which says that that generator raised to the 4th power is equal to the identity element in my group. Right? And so that really explicitly gives us the correspondence, that the same role that I plays in its group is the role that 2 plays within its group, which is the role that 0, -1, 1, 0 plays within its group. Algebraically, they are all acting the same in their structure, even if superficially those elements and their operations are very different. So here's the question I want to pose to you and give you a few minutes to work on this in your group today. What about the other group? How might we express that group using generators? How many generators would we need? What might the relations be that would explain how the other group operates? So that's this group right here. What I want to give you is just about 5 or 10 minutes to talk about that in your small groups here in just a moment. I don't have a place to put this. Actually, you can just create one in OneNote, I suppose. I'll create a blank page for you to write down your thoughts on this question inside of your OneNote collaboration space folder. So take about, let's say about 10 or 15 minutes to see if you could come up with a generators and relations presentation for this group, the third group in the 4-4s activity. Looking at this third group, and this third group had that unique property, unique to the 4-4s, right, in which each element in this group was its own inverse. If we multiply it by itself, it gives us the identity, right? And so the question is, what elements are necessary here in order to generate this entire group? Both necessary, but also sufficient, right? What is the smallest possible set of elements that once I have those elements, I necessarily get all the elements in my group because of closure. So your groups quickly figured out that we don't need to include the identity element as a separate generator because we always get the identity element as some power of my other elements, right? For example, A. As soon as we have A in my group, A times itself is equal to the identity, and so we necessarily have the identity because of the closure property. So we don't need the identity. It's not an independent generator of the other elements, right? We can always create the identity just by raising any of these elements to an appropriate power. But then the question is, do we need all of the other elements? Do they all make an independent contribution to the algebraic structure? Or can we explain the presence of one of them by the presence of the others, right? Is there a relation between those three elements, or are they all independent actors? And what did you all decide? On the question of whether all three of these elements are necessary to generate the group, the first thing that you noticed was the answer is definitely no, right? We can explain at least the presence of the element A comma B, which I'm going to call AB for the purposes of this discussion. We can explain why AB is in the group. It's there because as soon as we have A, And as soon as we have B, as long as we have both of those things, then when I multiply them together in the operation of this group, A multiply B gives me AB, according to this Cayley table, right? A operate B gives me AB. So as soon as I know that I have A and B, closure demands that we also have AB necessarily. Right? So there's a relation between those three elements that allows us to explain the presence of the third by the presence of the other two. Right? So we only need A and B to generate this group, because together, when I operate on them together, I get AB. And if I operate either one of them by itself, I get the identity element. And so therefore I have all four of the elements that we need for this structure. But then you took that a step further also and said, well, that's true actually of any two of the non-identity elements in this example, right? If I have A and I have AB, then I know I have the identity just by taking one and multiplying it by itself. But I also have B, because A operated on with AB gives me B. Right? And so if I have A and I have AB, then I necessarily have B as well. Right? And the same is true with B and AB. Right? So any two of those non-identity elements will generate the third one. And so a set of generators for this group can consist of any pair of those three non-identity elements. The simplest of which is, at least cognitively for us, right? At least the one that I like, that I think makes the most just cognitive sense, is we just call, A and B the generators, so that AB then we deduce from the presence of A and B. So then, if those are the generators, what then are the relations in this group? What are my cancellation laws? What are the words that I can spell with the alphabet A and B that I know I can just cross out because they're equal to an identity element? One of the first places you can go to look for relations, right, is just to take each individual element and ask, how many times must I multiply it by itself before I get back to the identity, right? And with each of the three non-identity elements in this group, that answer is twice, right? A times A gets me back to the identity. And so AA, or A squared, is an example of a relation. Likewise, BB is equal to the identity. So B squared is also a relation. AB is also a relation, right? Because that gets me back to the identity as well. So what we might say a presentation for this group might look like is it might look like this, right? We have two generators, A and B, and then we have these three relations, A squared, B squared, and AB squared, right? And we know for sure that those three expressions are all cancellation rules, right? We know for sure we can get rid of them. But now I want to ask the same question I asked you in your groups about the generators, which is, are all three of these relations necessary? Or can we deduce the truth of one of them from the truth of the others? In particular, let's see if we can decide whether or not the first two imply the third. If I know that A squared is the identity, and I know that B squared is the identity, can I convince myself that AB squared is equal to the identity? What I'm interested in answering is, do we have a cancellation rule that also tells me that this group has a commutative law? If A squared and B squared are both equal to the identity element, then can we also say that A times B is the same as B times A? Now, if we just look at the Cayley table that was put together here, we can directly check that A times B is AB, and B times A is also AB, right? And so the Cayley table could help us out here. And so that would have been, I think, the path of least resistance to proving this theorem. So maybe I'll write that piece out here real quick, and then we'll look at how could we have known that without the Cayley table as a sort of a separate question. Sorry, let's get some of this clutter off of my screen. And so here's the proof, right? Just by using the Cayley table, AB squared is A times B times A times B, right? It's AB times AB. But because of the associativity property of multiplication, which associativity holds by necessarily in every group, right? Those are the structures we work with. Associativity lets me go in and put a set of parentheses wherever I like in this expression. And I'm just going to put them in the middle, between the middle A and the B, right? And if I do that, now I can look in my Cayley table and say, well, what is B times A? I look in the Cayley table, B times A is AB, right? It's the set consisting of A and B. And so just by using my Cayley table, I can do that. Just trade AB, or trade BA for AB. Right? And now again, because of the associativity property, I can forget that there's parentheses there, and I can regroup my parentheses there, there. And now what? What is A times A? Identity. That's one of our cancellation properties. What's B times B? Identity. That's the other of our cancellation properties. What's identity times identity? By definition of identity, it's identity. Right? And so just by using the Cayley table, we can make this deduction. The question is, did we need the Cayley table for that? Or should we have known from the beginning that B times A will necessarily be equal to A times B? Does that follow just from having my first two relations? So let's take that proposition next here. I want to get that somewhere where my head's not blocking it. Let me move my head here real quick, and you can kind of go from there. There we go. So the thing that I was trying to reason us into as a lemma is something I'm actually not convinced anymore is true, and that is the statement that if I have two elements of a group A and B, and they both are elements of order 2, so they're their own inverses, then the conjecture was that those elements must commute with one another. But can we think of a time in our course where we have had an algebraic structure with two elements of order 2, and those elements of order 2 did not, in fact, commute one with another? If we can think of a counterexample, then this conjecture has got to be false. So here's an example from a few weeks ago. When we were building braidograms, even on a permutation of 3 letters, 3 elements, right? The permutation, for example, that takes the word now and changes it into some other word, right? One of the things we found out is that the transposition of the first and second strands of a 3-strand braid diagram, right? And the transposition of the second with the third, those elements, those transpositions did not commute one with another. If I did 1, 2 followed by 2, 3, as we have right here, I ended up changing the word now into the word own, O-W-N. Whereas if I did 2, 3 first followed by 1, 2, now gets changed into W-N-O. Right? So those are different anagrams. Therefore, 1, 2, and 2, 3 do not commute with one another, even though independently they are elements of order 2. Right? 1, 2 followed by 1, 2 gives me a permutation that doesn't actually change anything. Right? If I trade the first and second positions and then I trade them again, I end up back where I started. Same thing if I trade the second and third and then trade them again, I get back to where I started. But when those two interact with one another, they do so in a way that's not commutative. 1, 2 composed with 2, 3 is not the same as 2, 3 composed with 1, 2. So in fact, that counterexample convinces me of the necessity of all 3 of my relations. So this thing is false. E.g., 1, 2, and 2, 3 in the permutations of 3 do not commute. So what that tells me is that in fact we do need all 3 of these relations in order to describe the structure of the group G3, right? So we have 2 generators, A and B. As soon as I have A and B, I know necessarily I also have AB in my group, so I don't need all 3 as generators, but I do need all 3 of these cancellation rules in order to completely describe the structure that we have here. And that the structure that we get is the structure of that G3, that other group of 4 elements in which there cannot be a single generator that accounts for the structure of the entire group. So in total, what we found is that the groups G1, G2, and G4, they all had presentations, generators and relations, that looked exactly the same as one another. There existed a single element which can generate the whole group, right? And that element had a single relation, that element raised to the 4th power was equal to the identity. Done. Right? By way of terminology, if I have a group that has only a single generator in it, we call that group a cyclic group. Right, so a cyclic group is one where we can find a single element, single one of its elements, whose powers account for every single other element in the group. Right, so we call those groups cyclic groups, which means that the three groups which were the same in this activity, G1, G2, and G4, those were all cyclic groups because we could find a single element that generates everything. Whereas G3 was not a cyclic group. We didn't have just a single element capable of generating all the elements in that group. We in fact needed two. And in fact, in this example, any pair of the three non-identity elements can generate all the remaining elements in my group. But we needed both of them. And once we needed both of them, we also needed a separate relation for each one of those three non-identity elements that says that its second power is equal to the identity. And that gives me a complete set of cancellation rules for this group.